Okay, we're going to go over this group quiz that you guys took a while ago. I was going to return them at the end of the unit as a review for this material, since it's been a while since we've looked at this kind of thing. But we're not there, so I'm just going to go through each of these, go through how to answer it, the reasoning behind the answers, solve it, and so on. So here we go. So the first one, we have a proton moving the same direction as the electric field. So anytime I have a question like this, the first thing I'm going to do is I'm going to draw a picture of that. So it doesn't give us a specific direction, so I usually just draw the electric field to the right. The electric field always goes positive to negative, so I know this is the positive plate here, this is the negative plate here. And we have a proton moving the same direction. So I'm going to put a positive charge in here, go in the same direction as the electric field. Alright, and it's talking about potential energy and electric potential. So if you remember, electric potential is always high at the positive plate. So I'm going to say high V there, always low at the negative plate, so low V there. Always, doesn't matter what the charge is. Now for potential energy, it matters what the charge is. So the positive charge, it doesn't want to be at the positive plate. It really wants to spring away from that. So it's got a lot of potential energy, a lot of stored energy right there. So at the positive side, we're going to have high electric potential energy for a positive charge. And then the negative side, once the positive charge gets here, it's like a ball on the ground. It's going to sit there. It's going to have very low potential energy here. Okay, so to answer this question, as the positive charge is moving this direction, it's going from high potential to low potential, so its electric potential is decreasing. It's going from high potential energy to low potential energy, so its electric potential energy also is decreasing. So our answer is D. Alright, now number 2, electric potential energy is always high. Well, its energy is our key word there. It depends on what the charge is. Okay, so we just talked about in number 1, a positive charge has high electric potential energy at the positive plate. So that is answer C. Okay, at the positive plate if the charge is positive. A negative charge would have very low potential energy here because it's happy to be there. Negative charge would have high potential energy at the negative plate. So that answer is F. So our two answers there are C and F. Number 3, electric potential is always high at the positive plate. We just talked about that. In class we went through and showed that. I'm not concerned if you can go through and show that. That's something if you just want to remember, that'll get you through these problems. Alright, number 4, electric field directed in the negative Y direction. So I'm going to draw a picture. I always draw pictures. I've been doing this for a lot of years. I still draw pictures, so you should as well. So the electric field is going in the negative Y direction, so I know this side is positive, this side is negative, because again, electric field always goes positive to negative. And now we have a positive charge here, I'll put it somewhere in here, moving in the positive X direction, so it'd be like this. Okay, so it's asking the change in potential energy. So if you do not draw a picture, and if you just look at these numbers and find an equation and put them in and solve, you're going to get the wrong answer. A picture is huge in this case. So we can see the positive charge is not getting closer to the positive side, it's not getting closer to the negative side. We know it's going to have high electric potential energy here. Oops, that's the wrong letter. And it's going to have low electric potential energy here. Okay, well, it's not changing its electric potential energy. It's not getting higher, it's not getting lower. So in this case, our change in electric potential energy is 0. Okay, you could also look at the equation delta V equals delta EPE over Q. We're not getting to a higher potential, we're not getting to a lower potential, so this is 0. 0 equals 0 over whatever the charge is. Either way you look at it, we're not changing our potential energy in this problem. In order to change potential energy, you have to be either getting closer to the positive or closer to the negative. You have to be moving some direction parallel to the electric field. Okay. Number 5. We've got a uniform electric field in the positive x direction. So, drawing a picture. This will be positive, this will be negative. Okay, electric field's going that way. Positive charge moves from the origin, so somewhere in here, and then to the point 25 centimeters, so it's going to be moving to the right. So it's moving with the electric field. What is the change in potential energy of this charge? Well, it is going to have a change in potential energy because it's moving parallel to the electric field, so we need to solve for that. Alright, for that I'm going to use the equation delta EPE equals plus or minus QED. Okay, if you remember, QE is the force and D is the distance. Force times distance is work. Work is the change in potential energy. That all ties together. Okay, the plus or minus, we're talking about a positive charge. Okay, so just like we talked a minute ago, it's going to have high energy at the positive plate and low potential energy at the negative plate. Alright, so right now I know I'm going to have a decrease in potential energy because we're going from higher to lower. So when I plug in the numbers, I've already made that decision it's going to be negative because it's a decrease in potential energy. It's a negative change. So my charge is 12 microcoulombs, so 12 times 10 to the negative 6. You all remember micro is negative 6, right? The electric field strength, 520 newtons per coulomb, and then the distance, 25 centimeters. Again, make sure you're in meters. You guys know that. So then we get a change in potential energy of negative 0.00156 joules. Alright, and then part B, through what potential difference, remember that's delta V, through what potential difference does the charge move? So two ways we could look at this. Delta V equals plus or minus ED, or we could say delta V equals delta EPE over Q. We just solved for delta EPE, so you could put that in there. We know Q, put that in there. You're going to get the right answer. I'm going to use this approach. Okay, so delta V equals, so plus or minus ED. Well, we're going from the positive to the negative. So remember, V, electric potential, is always high at the positive and low at the negative. So if we're going positive, negative, we're decreasing our electric potential, or we have a negative change in electric potential. The electric field strength, 520, the distance, 0.25. So here, our potential difference, negative 130 volts. Alright, number 6. Recharged a battery. We're moving some charge here. How much work is done? Okay, well, work, if you recall, is the change in energy. Okay, and in this case specifically electric potential energy. So if we solve for that change in energy, we know that's going to equal the work. So I'm going to say delta V equals delta EPE over Q. And I'm using this equation because I have the V and I have the Q and I need the delta EPE. So this one's pretty straightforward. So 21 volts equals what we're looking for over the charge, 3.6 times 10 to the 5. So we solve that for a change in electric potential energy that will equal the work done, and we get 7,560,000 joules. That's that. Alright, number 7. Electron released from rest in a uniform electric field. Strength is 9,500 newtons per coulomb. Through what potential difference will have passed after moving 1 centimeter? Charge, moving an electric field, picture. Okay, so we're not told up, down, left, right, positive, negative. So like I said earlier, I usually just draw it to the right. It's my habit. So this is positive, this is negative. We have an electron released. Well, which way is the electron going to go? It's going to be attracted to the positive, repelled from the negative, so it's going to move this direction. Alright, so again, we know positive side, high electric potential always, negative side, low electric potential. Now, because it's a negative charge, it's going to have high potential energy at the negative side. And it's going to have lower electric potential energy at the positive. Okay, so we get the picture. Now we want to know the potential difference. So part A. We're given the electric field and we're given the distance. So if you look at your equations, plus or minus ED is going to be what we want to work with here. Alright, now the negative charge is moving towards the positive, so we see it's going to get a higher electric potential, so its change in potential should be positive. So positive electric field strength 9.50 times 10 to the third. That's 0. And then the distance 1 centimeter, make sure you're in meters, so 0.01. So our change in potential is going to be a positive 95 volts. Part B. What's the change in potential energy? Okay, well now I know delta V, I know the charge, I know a lot of stuff now. So find an equation that will fit your information. So I'm using delta V equals delta EPE over Q. Alright, delta V we just solved for, 95. Delta EPE is what we're looking for. And then Q, our charge, is an electron, so it's negative 1.6 times 10 to the negative 19 coulombs. So I solve for my change in electric potential energy. Mathematically, I get a negative. I'm going to go with that for right now. So 1.52 times 10 to the negative 17 joules. Now, the negative, I never really trust the math. I'm going to go back to my picture and make sure it makes sense. So I have the electron, the negative charge, is moving towards the positive. So it's decreasing its potential energy. So the change in potential energy should be negative. That makes sense. So I'm going to go with that. Alright, and then part C, how fast will the electron be moving after it's traveled 1 centimeter? Okay, so this type of question, sometimes you can go through forces and acceleration in kinematics. You can also use the change in potential energy equals the negative change in kinetic energy. I will say not every problem you're going to be able to use the kinematics route. The energy, any problem we're dealing with in this class is always going to work. So that's what I'm going to go to. So I'm going to say the change in potential energy equals the negative change in kinetic. In other words, it's losing potential energy. It should gain kinetic energy. So it's going to gain 1.52 times 10 to the negative 17 joules of kinetic energy. Okay, if you remember, kinetic energy equals 1/2 mv squared. So 1.52 times 10 to the negative 17 equals 1/2. An electron, mass of an electron, 9.11 times 10 to the negative 31 kilograms. V squared. Solve that for V, and you should get 5.78 times 10 to the 6, that's a 6, meters per second. So moving pretty fast. Okay, there we have it. That's the group quiz. Make sure you understand the reasoning behind all this. If anything is confusing, look at it again, rewind the video, and then if you're still confused, shoot me an email. I'll be happy to discuss that with you.